All right, we are going to review and talk about area and volume today. So starting with area. So this occurs when you're talking about area between curves. So this is different than just an area with an x-axis, or what's the area under the curve. That's different. This is area between two curves. And when we are doing this, some kind of key things to remember is you are going to always have positive answers now, because you're doing the area of a shape, and your shapes are going to have a positive area. No matter what quadrant, where it is, doesn't matter. You are always going to get positive answers. Okay. So the first way we could break it down is we could look at it as like a top function minus a bottom function. And when we did that, everything was in terms of x then. So your bounds were x's, your ended with dx. These were functions of x. It was pretty straightforward. If it wasn't, or something that kind of didn't really have a top bottom, but more had a right or left, that's when we did it in terms of y. So your bounds were y, you had dy at the end. And all of these started from graphing your functions and finding that bounded area. So you've got to start by drawing the graph, unless it's given to you, and seeing what the shape looks like. The last part with this that kind of showed up is sometimes it switched. So the function that was on the top and the bottom switched, or you had different sides to things. And that was the case. You had to break up into pieces if those functions were switching. And by pieces, we really mean integrals then, because that is what is finding those areas. And then again, all goes back to having a good, accurate graph that you can actually see where things are located. If it's on your calculator, you might need to zoom in if you need to kind of see where the sides are, and all of those things. Okay. With volume, that came into play next then, because really what we're integrating is the area of a cross-section. Okay, so there's a couple different types of cross-sections we had, so we'll kind of break those down, and then we'll do, I think I have 2 or 3 examples total with all of this. So the first part was if we had a circular cross-section, and that happened when we were rotating around some axis, whether it be the x, the y, or a different line that was moved, up, down, right, or left. Okay. In that subdivision of cross-sections, one of the type of cross-sections then was like that solid disc, when we were totally flush to our axis. So if it was butting up right to the thing you're spinning completely, that created this disc. And when that happened, it was one of these 2 options. So this is like 1 and 2 here. So what we're spinning is the cross-section is an area of a circle, so that's the pi r squared. And then the r usually just came from your function. And what was different is if we were going around something parallel to your x-axis, we did everything in terms of x. Your bounds were x's, your function was in terms of x, and usually your function was this big r there, and then it was squared. If we were spinning around something parallel to your y-axis, that is when everything changed to in terms of y. So you had y bounds, you were doing, everything was, your function was in terms of y, so it was x equals, all of those things. Okay. And just like the last part, these all start with graphing your functions and seeing, okay, what are the bounds, what am I spinning around, and kind of all of those details that go into that. All right, second type then of your circular cross-section was that you had a washer. The washer was when you were not flush to that axis of rotation. Okay, and so moving that there so you kind of see the last part. When that happened, we had 2 radii. So you had an outer radius and the inner radius that was scooping out the volume as the 2 lines or 2 parts spun. Okay. And so I'll give you a second to write all that down. Okay, the second option for cross sections was that you had non-circular cross section. And that's when you had a triangle popping up, you had a semicircle, a rectangle, a triangle, a square, something that was described. Okay. Now in this case, when we did this, we're still integrating the area of a cross-section. That did not change. What's a little bit different is what your variable is, and it all depended upon what you were perpendicular to. So if you were perpendicular to your x-axis, it was all in terms of x. And if you were perpendicular to your y-axis, everything's in terms of y. So again, functions in terms of y, the area of the shapes in terms of y, bounds are y's, all of that. Notice these do not have pi's. I'm not squaring my area. Could something squared show up in there? Yes, but that's only because of the area formulas for these shapes. Maybe you had the area of a square, so you had something squared, but that's only because it was a square. So no spinning in these ones. These are more your popping out shapes. All right, let's get to an example. So if you want to, try these, I would hit pause, try this completely on your own, then hit play, and I'll talk through the solution. But it might be a good strategy to try it on your own. Also try it without using a calculator, because I know we did these all with a calculator, but not everyone will have a calculator with it. So you want to be able to practice both ways as we're preparing for the AP test. All right, hopefully you actually hit pause and didn't just keep watching this. All right, so to start off with, we got to get a graph. So I know without a calculator, this is going to have zeros at 0 and -5 because of how it would factor. So here's at -5, and I know my parabola is going to open up because I have a positive a value. This one is going to be that parabola opening down because there's my negative a value starting from up 3 to 3. And so I'll use a highlighter here. Here is my area. So as I'm looking at this, I just want area, so no volume involved in this one. When I look, I can see that my top function is always this parabola that's upside down. And so I can see that this is going to be fine to do top minus bottom, which means we're going to be doing these things in terms of dx with x values as my bounds. You can do it right and left, but if you notice, your right side switches right here, and you've got different functions on the right, and so you'd have to do 2 integrals if you did it in terms of y. So I'm going to stick with the easier one and do it in terms of x. So I'm going to start by finding my bounds. So I've got x squared plus 5x equals 3 minus x squared. So moving that all over, 2x squared plus 5x plus 3 equals 0. I'm hoping I can factor that. Let's see, be plus 3 minus 1. So my intercepts are a half and -3. Okay. So I've got -3 to a half. And then it's top minus bottom. So my top is the 3 minus x squared minus my bottom, making sure I put the bottom in parentheses there. So x squared plus 5x. Now to do my antiderivative, and I'm going to do it by hand because we need to make sure we know that, I'm not going to do it just like this. I'm going to combine some like terms first. So I'm going to keep my -3 to a half. I'm going to, order doesn't really matter, but this will be minus 2x squared, and this is now minus 5x dx. Okay, so taking my antiderivative, this is a straightforward antiderivative, so power up to 3x. Whoops. There we go. Minus 2x cubed over 3, and minus 5x squared over 2. And then now I'm evaluating from -3, sorry, my thing's messing up here, to a half. Okay. Now, if this is a free response, you don't, you have to plug these numbers in, but you do not have to actually simplify. So this would be 3/2 minus 2, I'm just going to put the 2/3 kind of out front here. And then I'd have a half cubed minus 5 halves. I can square that in my head if I want, so that's a 4th squared. And then minus, so now I'm going to plug my -3 in there. So I would have -9 minus 2/3 -3 cubed minus 5 halves. And -3 squared is 9, so I can put a 9 there. Close that a little earlier. And so if it's free response, you can leave it like that. If it's multiple choice, you're going to have to probably do some simplifying, but with writing this as 2/3, a half isn't 2, or it's an 1/8. And so some of this will probably combine and cancel, and it won't be too crazy if it's multiple choice. All right, next one, let's do a volume. It says the volume of the region bounded by my parabola, my line, is rotated around -3. Okay. So I read that and I go, okay, I am rotating. So is this circular or non-circular? Well, if I'm rotating, this needs to be that circular, circular one. Okay, so I start my graph. My zeros, so this is going to be parabola. It goes through 0 and 4, and then opens down. Okay, y equals 0 is this part here. So my contained section is right here. Okay, I want to go around the y equals -3 line. 1, 2, 3. So from there, I need to decide, okay, is this in terms of x? You know, is this dx or dy? Well, it's just the x-axis dropped down, so it's dx. Is this a washer or a disc? Okay, I'm not flush, so this is a washer. Okay, so one recommendation was maybe do your radii separate, and then, you know, put it all into the integral at the end. So my outer radius is being defined by my parabola to this dotted line. So the height to my axis is my parabola, and then there is 3 more to the next part. Okay. The other way to think about it is it's top function minus bottom. Your top is your parabola minus -3 is your +3. Okay, my inner radius here, well, that would just be 3 because it's 0 minus -3. Okay, so my integral then, I'm going to put a pi because I'm spinning 0 to 4 for my x's, and it is outer radius, so 4x, if I'm going to need parentheses, minus x squared plus 3 squared, and then minus 3 squared dx. Okay, and that's one that you might have a calculator on. You know, maybe you foil that. That wouldn't be too bad of a foil, and do a power up, power over. Good chance that would end up on a calculator section of the multiple choice if it was on multiple choice. So you wouldn't have to do all that, but potentially you would. All right, maybe pause this one and try this one then. This one we have cross sections that are rectangles. So this is going to be the non-circular type that we've got. So maybe give this a try. When you're ready, hit play. All right, find the volume. We got our base is created by these two functions. So I have a square root that's going negative, and I have a line with a down 1 over 2 negative slope. So my graph isn't super big, but I'm going to be right in here. Okay, and then my cross sections are rectangles. Whoops, I want to back again, sorry. Are rectangles, and the height is perpendicular to the x-axis. I can't read, sorry. Okay. Now after I draw this, it's a good practice to just go and reread it and make sure you've got it started right. Let's find the volume of the solid whose base is bounded by the region, these two functions. So that looks right. Cross sections are rectangles of height 3. Okay, so I missed that part. The height of this is 3, and they're perpendicular to the y-axis. So they're going this way. All right, so when I do this, then I go, all right, what am I, so really these rectangles are going to slide side to side. So if I'm sliding side to side, that would be dx, because I'm perpendicular to the x-axis. Okay, I need to figure out how long this part is, because those two things correlate together. Well, if I think of it as, it'd be the top minus bottom idea. So my top is my -1/2 x, and my bottom is my, so it'd be minus negative square root of x, and so that would be my base. Okay. I do need to find where those intersect. So let's set them equal to each other. So I'd have negative square root of x equals -1/2 x. I'm going to divide the negative off, just to make life easier. Squaring. I very carefully make this 1/4 x squared, because I have to square this side, and the half is on the side. Okay, so then moving x over, so if I subtract x over, factor, I have 1/4 x minus 1 equals 0. 1/4 x. Make sure I did that right, sorry. Taking out x, oh, yep. Okay, so I have x equals 0. I would add 1 and multiply by 4. So I have 0 to 4. Okay, my area of my rectangle is base times height, x plus the square root of x, and then dx. So if there's no pi, I don't square anything, because your height is 3, and your perpendicular axis length here is top minus bottom. So it's that negative 1/2 x plus the square root of x. Okay. And that would be another one. You do not need a calculator to do this question. Either way, I'll distribute the 3, we'll say. So I'm 0 to 4, I'd have negative 3/2 x plus 3x to the 1/2. Okay, my antiderivative then, over 2, I would power up to 2 over 2. This one would go power up to the 3/2 over 3/2, and then evaluate from 0 to 4. Okay, doing some simplifying, it'd really be negative 3 over 4, and then I'll put 4 squared here. So plugging 4 in, plus, so this would be 3, so the divided by 3 has a flip up to 2/3, so really that's just a 2 then. So 2, and then I'd have 4 to the 3/2, and then minus, that stuff was 0, but 0 to all those powers would go away. Okay, now simplifying this, so I've got, you know, one of these 4s would cancel, so this would be negative 12. So that's how I did that. This would be like 16 over 4, and then 4 squared is 16 over 4, would just be a times 4 then. Now on this one, you might be like, how do I do that power? Well, you can do the square root first. So you can do the square root of 4 and then cube it. So the square root of 4 is 2, cubed is 8. So this thing is just 16 then, 8 times 2. So this just gives you 4 along the way. Okay. All right, keep working on that book, and we'll keep chipping away at this.